Welcome back to Whispering Universes, where tonight we turn our attention not to the stars above, but to the depths below. We're going to explore the deepest place on Earth, a realm so remote, so crushing in its pressures, that fewer people have visited it than have walked on the moon. The Mariana Trench lies at the bottom of the Pacific Ocean, more than 36,000 feet beneath the waves, and it represents perhaps the last true wilderness on our planet, a place where darkness has reigned unbroken for hundreds of millions of years. Consider for a moment the paradox of our modern age. We've sent rovers to Mars, captured images of galaxies billions of light years away, and mapped the cosmic microwave background radiation from the birth of the universe itself. We can peer backward in time nearly to the Big Bang. Yet, here on Earth, the vast majority of our ocean floor remains unexplored, unmapped, and unknown. The Mariana Trench, specifically, is farther from the surface world than the International Space Station is from the ground. When you're standing at sea level looking down, you're closer to the astronauts orbiting overhead than you are to the creatures moving through the Hydrothermal zone 7 miles beneath the waves. The numbers themselves seem almost unbelievable. If you could somehow take Mount Everest, that ultimate symbol of earthly height, and place it at the bottom of the Challenger Deep, the deepest point in the Mariana Trench, its peak would still be covered by more than a mile of seawater. The pressure at these depths exceeds 15,000 pounds per square inch, more than 1,000 times the atmospheric pressure we experience on the surface. It's equivalent to having 50 jumbo jets stacked on top of your thumbnail, a force so immense that it challenges our imagination and pushes the boundaries of what we thought possible for life. And yet, life exists there. Against all expectations, the bottom of the Mariana Trench teems with organisms, from microscopic bacteria to fish and crustaceans, all adapted in remarkable ways to an environment that seems fundamentally hostile to biology as we know it. The trench isn't a barren wasteland, but an ecosystem, different from anything else on Earth, shaped by millions of years of evolution in isolation and extreme conditions. Tonight, here on Whispering Universes, we're going to make a journey downward through the ocean's layers, past the zones where sunlight penetrates, beyond where most fish can survive, into the realm of eternal darkness and pressure. We'll explore how the trench formed in the first place, carved into the seafloor by the slow grinding of tectonic plates. We'll meet the extraordinary creatures that call this abyss home, organisms that have solved the puzzle of survival in ways that challenge our understanding of biochemistry itself. We'll learn about the handful of brave explorers who've descended into this darkness, and we'll confront the uncomfortable truth that even here, in the most remote place on Earth, humanity's mark is visible. The Mariana Trench reminds us that our planet still holds mysteries, still contains places where the unknown isn't theoretical, but actual, where scientists make genuine discoveries, not by looking at data from distant telescopes, but by sending cameras and sensors into depths that remain, for the most part, as alien to us as the surface of another world. It's a humbling thought, and perhaps a comforting one as well. Earth isn't fully known. There are still frontiers here, still questions to answer, still wonders to discover, without ever leaving our home planet. So let's begin our descent. Let the surface world fade above us as we sink through layers of ocean, each one stranger than the last, until we reach the bottom of the world, where life has found a way to persist in what should be, by all accounts, impossible conditions. Let's explore what's hidden beneath the Mariana Trench, and in doing so, perhaps discover something about the tenacity of life itself, its ability to adapt, to survive, to thrive in places we never imagined possible. The Mariana Trench didn't appear suddenly. It's the product of a geological drama that's been playing out for tens of millions of years, a slow-motion collision between massive sections of Earth's crust that continues even now as you listen to these words. To understand the trench, we need to understand plate tectonics, the fundamental process that shapes our planet's surface and drives everything from earthquakes to mountain building to the creation of deep ocean trenches. Earth's outermost layer, the lithosphere, isn't a single, unbroken shell, but a mosaic of large plates that float on the partially molten rock of the mantle beneath. These plates move, sliding past one another, pulling apart or pushing together at speeds measured in centimeters per year, about as fast as your fingernails grow. It sounds slow, but over millions of years, these tiny movements reshape continents, open and close ocean basins, and build mountain ranges that scrape the sky. The Mariana Trench formed at what geologists call a subduction zone, a place where two tectonic plates meet and one slides beneath the other, descending back into Earth's interior. Specifically, the western edge of the Pacific Plate, which carries some of the oldest ocean floor on Earth, is sliding beneath the smaller Philippine Sea Plate. As the Pacific Plate bends downward and begins its descent into the mantle, it creates a deep depression in the seafloor. The trench itself, marking the boundary between these two great sections of crust. This process of subduction is fundamental to how our planet works. Earth is the only rocky planet in our solar system with active plate tectonics, a fact that may be intimately connected to the presence of liquid water on the surface and, ultimately, to the existence of life itself. The Pacific Plate carries with it not just rock, but water, trapped in minerals and sediments, and as it descends into the hotter regions of the mantle, that water is released, lowering the melting point of the surrounding rock and contributing to the volcanism that creates island arcs like the nearby Mariana Islands. The Pacific Plate at the Mariana Trench is ancient, formed at mid-ocean ridges more than 180 million years ago during the Jurassic period, when dinosaurs roamed the continents and the Atlantic Ocean was just beginning to open. This old ocean floor is cold and dense, which makes it heavy enough to sink when it encounters another plate. As it descends, it carries with it a record of those 180 million years, sediments that accumulated grain by grain, the remains of countless microscopic organisms that lived and died in the surface waters and drifted down to the seafloor. The geometry of subduction zones creates their characteristic features. The trench itself is the deepest part, the point where the descending plate first bends downward. On the landward side of the trench, the overriding plate often develops a series of underwater ridges and basins. Further inland, you typically find a chain of volcanic islands, created by magma, rising from the depths, where water released from the subducting plate triggers partial melting. The Mariana Islands themselves are products of this process, each volcano fed by rock that was once part of the Pacific seafloor and has been recycled through the mantle. Geologists have calculated that the Pacific Plate is descending beneath the Philippine Sea Plate at a rate of about 2 to 3 centimeters per year. It doesn't sound like much, but it means that every human lifetime, the plate moves about 2 meters deeper into the Earth. Over the millions of years this process has been active, vast amounts of ocean floor have been consumed and recycled. The oceanic crust that exists now at the Mariana Trench will, in 100 million years, be hundreds of kilometers beneath the surface, its minerals transformed by heat and pressure into new forms, perhaps eventually to rise again as volcanic rock on some future island or continent. The trench, then, is a wound in the Earth, but a wound that's part of a healing process, a natural cycle that recycles oceanic crust, regulates the planet's chemistry, and drives the geological activity that may have been essential for the development and maintenance of life. Standing at the edge of the trench, if such a thing were possible, you'd be witnessing one of the fundamental processes that makes Earth a living, dynamic world rather than a static, dead sphere of rock like Mars or the Moon. This is where our journey begins, at the convergence of two great plates in a place where Earth folds back on itself and creates, in the process, a portal to depths that challenge everything we thought we knew about the limits of the possible. To reach the bottom of the Mariana Trench, we must first descend through the ocean's vertical structure. passing through zones that might as well be different worlds, each with its own characteristics, its own forms of life, its own relationship with light and pressure and temperature. Let's make that journey now, slowly, layer by layer, as the world above grows dimmer and the pressure increases with every meter of depth. We begin at the surface in what oceanographers call the epipelagic zone, or more poetically, the sunlight zone. This extends from the surface down to about 200 meters, and it's the realm most familiar to us, the ocean of documentaries and scuba diving, where light penetrates strongly enough for photosynthesis. Here, phytoplankton, the microscopic plants of the sea, capture the sun's energy and form the base of nearly all ocean food webs. The water is relatively warm, especially in tropical regions like that above the Mariana Trench, and it hosts the greatest diversity of life in the ocean, from tiny planktonic organisms to the largest animals ever to exist on Earth, the great whales. As we descend past 200 meters, we enter the mesopelagic zone, the twilight zone, where sunlight becomes increasingly faint. By the time we reach 300 meters, we're in a dim blue world where colors begin to lose their meaning. Red light has been absorbed completely by the water above. Orange and yellow have followed. Only blue-green wavelengths penetrate this deep, creating an eerie, monochromatic landscape. Many of the animals here have large eyes, adapted to gather whatever faint light remains. Others have given up on vision entirely, or produce their own light through bioluminescence, creating an alien light show in the gloom. The twilight zone extends down to about 1,000 meters, and it's here that we encounter one of the ocean's most extraordinary phenomena, the vertical migration. Every night, countless organisms rise from these depths toward the surface to feed, then descend again before dawn, the largest migration of biomass on the planet, happening twice every day in oceans around the world. The animals making this journey include small fish, squid, and especially copepods and krill, tiny shrimp-like creatures that can number in the millions per cubic meter of seawater. Below 1,000 meters, we enter the midnight zone, the bathypelagic realm, where the last traces of sunlight are extinguished completely. This darkness isn't like the darkness of a moonless night on land, where your eyes might eventually adjust and perceive faint shapes. This is absolute darkness, the complete absence of light, a condition that has persisted here for millions of years, broken only by the occasional bioluminescent flash of a deep-sea creature. The pressure here exceeds 100 times surface atmospheric pressure. The temperature drops to just a few degrees above freezing. Life becomes sparser, but no less remarkable. The fish here often have huge mouths and elastic stomachs, adaptations for swallowing prey that might be larger than themselves, because food in the deep ocean is scarce, and you can't afford to pass up a meal just because it's big. Many species are black, a coloration that makes them nearly invisible against the background darkness. Others are transparent or have reflective surfaces on their undersides to match any faint downwelling light, a camouflage technique called counter-illumination. At 4,000 meters, we transition into the abyssal zone, the realm of the abyssal plains, those vast flat regions that cover much of the deep ocean floor. The pressure here approaches 400 atmospheres. The water temperature hovers around 2 degrees Celsius. The sediments on the seafloor accumulate at rates measured in millimeters per 1,000 years, each layer recording tiny changes in ocean chemistry, climate, and biology. These sediments are archives of Earth's history, and scientists core them to read that history, learning about past ice ages, volcanic eruptions, and even asteroid impacts from the chemical signatures trapped in the mud. But we're not stopping at the abyssal plain. We're going deeper into a final zone that represents less than 2% of the ocean floor, but holds a significance disproportionate to its size. Below 6,000 meters, we enter the Hadal zone, named after Hades, the ancient Greek underworld. This is the realm of ocean trenches, and the Mariana Trench is the deepest of them all. The Hadal zone is defined by its extreme depth, and with that depth comes pressure that exceeds 600 atmospheres and can reach more than 1,000 atmospheres in the deepest spots. The Hadal zone remained completely unknown to humans until the mid-20th century. It's a region so extreme, so difficult to access, that it's been explored less than the surface of Mars. The animals living here face challenges that push the limits of what biochemistry can achieve. And yet they not only survive, they've diversified into unique species found nowhere else on Earth. The sediments here are different too, less disturbed by currents, accumulating in a stillness that's hard to imagine. A quiet broken only by the occasional rumble of an earthquake, as the plates beneath continue their ancient, slow collision. This is the layered architecture of the ocean, a vertical world where conditions change more dramatically with depth than they do with distance across the surface. And now, having descended through all these zones, we're ready to reach the bottom, to explore that ultimate realm where Earth's crust folds back on itself and creates the deepest natural point on the planet's surface. The Challenger Deep, the deepest known point in the Mariana Trench, lies at approximately 10,994 meters below sea level, though exact measurements vary slightly depending on the equipment and methodology used. That's 36,070 feet, or nearly 7 miles of water above the sea floor. To put this depth into perspective, imagine taking Mount Everest, which rises 8,149 meters above sea level, and inverting it, placing it upside down in the trench. Its peak would still be covered by more than 2,000 meters of water. The summit of Everest, that symbol of ultimate earthly height, wouldn't even reach the lower bathypelagic zone if submerged in the Challenger Deep. The pressure at this depth is almost incomprehensible from a human perspective. On the surface, at sea level, we experience about 14.7 pounds per square inch of atmospheric pressure, the weight of the column of air above us extending to the edge of space. We don't notice this pressure because we evolved in it. Our bodies are adapted to it, filled with fluids and gases that balance it perfectly. But water is much denser than air, and with every 10 meters of depth you descend in the ocean, you add another atmosphere of pressure. By the time you reach the Challenger Deep, the pressure exceeds 15,000 pounds per square inch, more than 1,000 times surface atmospheric pressure. What does this pressure feel like? Imagine placing 50 Boeing 747 aircraft on top of your thumbnail. That's roughly the force pressing down on every square inch of surface area at the bottom of the trench. It's a force that would instantly collapse any air-filled space, crush any conventional submarine, and squeeze the gas out of human lungs and bloodstream so completely that survival would be impossible without technology as sophisticated as that used in spacecraft. This pressure changes the properties of water itself. At these depths, water becomes noticeably more viscous, slightly thicker. Its freezing point drops below the 0 degrees Celsius we know at the surface. The speed of sound in water increases, reaching about 1,150 meters per second, compared to roughly 1,080 meters per second at the surface. These might seem like small changes, but they affect how sound travels through the ocean, how animals communicate, and how we use acoustic instruments to map and study the deep sea. The temperature at the bottom of the Challenger Deep stays remarkably constant, hovering between 1 and 4 degrees Celsius, just a few degrees above the freezing point of seawater. This cold is perpetual. The water here has never felt the warmth of the sun. It's old water, part of deep ocean currents that take hundreds or even thousands of years to complete their circulation through the world's oceans. Some of the water molecules at the bottom of the trench may have last been at the surface before humans invented writing, before the pyramids were built, perhaps even before the last ice age ended. And then there's the darkness. We often use darkness metaphorically, talking about the darkness of night or a dark room, but these are nothing compared to the absolute, complete darkness of the Hadal zone. No photon of sunlight has penetrated to these depths for hundreds of millions of years, not since this water was last at the surface during some previous great cycle of ocean circulation. The only light here comes from biology, the bioluminescent flashes of deep-sea organisms, brief sparks in an otherwise eternal night. In this environment, isolated by depth and pressure, cut off from the energy of sunlight, it would seem impossible for life to exist. The conventional wisdom for much of human history held that the deep ocean must be a lifeless desert, too dark, too cold, too crushing for anything to survive. The discovery that this assumption was wrong represents one of the great revelations of oceanography, a finding that has implications not just for understanding Earth, but for considering the possibility of life in the subsurface oceans of moons like Europa or Enceladus, where similar conditions of darkness, pressure, and cold might also support living ecosystems. The Challenger Deep is named after the HMS Challenger, the British Royal Navy ship that conducted the first major scientific expedition to study the deep ocean in the 1870s. Using hemp rope and lead weights, the Challenger expedition made soundings that revealed the existence of extremely deep trenches, though they lacked the technology to reach the bottom or understand what they'd found fully. It would be another 80 years before humans actually reached these depths. And even now, more than a century and a half after the Challenger expedition, we've barely scratched the surface, so to speak, of understanding what exists in these abyssal realms. 7 miles down, it's a distance that seems almost mythological, a depth that challenges our imagination and technological capabilities in equal measure. And yet it's real, a physical place on our planet, accessible with sufficient engineering and courage. The question isn't whether we can reach it anymore. The question is, what will we find when we look more closely at what's hidden at the bottom of the world? The Mariana Trench isn't a simple crack in the seafloor, but a complex geological feature that stretches across more than 2,550 kilometers of the western Pacific Ocean, forming a long arc parallel to the Mariana Islands. If you could somehow drain all the water from the Pacific and stand on what's now the ocean floor, you'd see the trench as an immense canyon, a scar in the Earth's crust that dwarfs any similar feature on land. The Grand Canyon, that iconic chasm in Arizona, would fit inside the Mariana Trench with room to spare, its depth less than half that of the trench at its deepest point. The trench has a characteristic shape, common to subduction zones around the world. On one side, the seaward side, the slope is relatively gentle, about 4 to 8 degrees, following the curve of the Pacific Plate as it begins its descent into the mantle. On the other side, the landward side closer to the Mariana Islands, the slope is steeper, sometimes exceeding 10 degrees. This asymmetry reflects the different geological processes at work. The gentle slope is the bending of the incoming plate, while the steep slope is the edge of the overriding plate, deformed and thrust upward by the forces of collision. Within this great arc, there are multiple named deep points, places where the trench bottom reaches exceptional depths. The Challenger Deep, which we've already discussed, is the most famous and the deepest. But there's also the Serena Deep, which reaches 10,714 meters, and the Horizon Deep at 10,816 meters. These aren't separate trenches, but rather the deepest points within different sections of the Mariana Trench system, like valleys within a larger valley. Each one has been visited only a handful of times, and vast stretches of the trench floor between them remain unexplored. Modern mapping technologies have revealed that the trench floor isn't smooth and featureless, but has its own topography, its own smaller ridges and depressions. Multi-beam sonar, which sends out a fan of sound waves and measures their return time to build up a three-dimensional image of the seafloor, has shown underwater mountains rising from the trench floor, some reaching heights of hundreds of meters. These seamounts create localized habitats, places where currents might be slightly different, where sediments accumulate in particular patterns, and where the biological community might be distinct from the surrounding areas. The sediments in the Mariana Trench tell their own story. In most parts of the deep ocean, the seafloor is covered by a layer of soft sediment composed largely of the shells and skeletons of microscopic organisms that lived in the surface waters and drifted down after death. This biogenic ooze can be hundreds of meters thick and accumulates at rates of about 1 to 2 centimeters per 1,000 years. In the Mariana Trench, however, sediment accumulation is more complex. Some areas have thick sediment deposits, while others show bare rock, the result of underwater landslides that periodically send sediments cascading down the trench slopes or currents that sweep certain areas clean. These sediments are of great interest to scientists because they contain records of earthquakes, volcanic eruptions, and even tsunami events. Layers of coarser material, such as sand or gravel, in an otherwise fine-grained sediment sequence indicate sudden catastrophic events, turbidity currents triggered by earthquakes that roared down the trench slopes, carrying sediment from shallower depths. By coring these sediments and analysing their composition and structure, researchers can reconstruct the seismic history of the region going back thousands of years, information that's vital for understanding earthquake risk in the populated islands nearby. The trench also has a chemical signature. Water samples taken from the Challenger Deep show slightly different chemistry compared to seawater from other parts of the ocean, with elevated levels of certain dissolved gases and minerals. Some of this chemistry comes from the geological activity, the interaction between seawater and the rocks of the descending plate. Some comes from the breakdown of organic material in the sediments, and some remains mysterious, hinting at processes we don't yet fully understand. One of the remarkable aspects of modern ocean exploration is how technology has changed our ability to see these hidden landscapes. In the 1950s and 1960s, when the first deep-sea trenches were being explored, mapping meant lowering a weighted line and recording the depth when it hit bottom, then moving the ship and repeating the process. It was slow, laborious work that could take years to map even a small area with any detail. Today, autonomous underwater vehicles equipped with sophisticated sonar can map hundreds of square kilometers in a single mission, revealing features that would have taken decades to discover with older methods. Yet, even with modern technology, the Mariana Trench remains largely unmapped at high resolution. The deepest parts have been surveyed, yes, but vast stretches of the trench floor are known only from low-resolution sonar scans that can't reveal details smaller than hundreds of meters across. It's entirely possible, even likely, that there are features in the trench, hydrothermal vents, unusual rock formations, or distinct biological communities that we simply haven't found yet because we haven't looked in the right place or with sufficient detail. The shape of the abyss, then, is both known and unknown, mapped in broad strokes but mysterious in its details. A landscape that's both ancient, formed over millions of years, and dynamic, constantly being reshaped by earthquakes, landslides, and the slow but relentless movement of tectonic plates. It's a reminder that Earth's surface is not fixed but flowing, changing on timescales both geological and immediate. The water filling the Mariana Trench isn't fundamentally different from the water in other parts of the ocean. It's the same H2O molecules, the same dissolved salts, but the extreme conditions at these depths give it properties and characteristics that make it unusual. A medium that's been shaped by pressure, darkness, and isolation in ways that affect everything from its chemistry to the life it supports. Let's start with the basics. Seawater is a solution, a mixture of water molecules and dissolved substances, primarily salts. The average salinity of ocean water is about 35 parts per thousand, meaning that in every kilogram of seawater, there are about 35 grams of dissolved salts, mostly sodium chloride, table salt, but also magnesium, calcium, potassium, and many other elements in smaller quantities. This salinity remains relatively constant throughout the ocean, including in the deep trenches, because the ocean is well mixed over geological timescales. Water that sinks from the surface eventually mixes with water from other parts of the ocean through a global system of deep currents, sometimes called the thermohaline circulation, or the ocean's conveyor belt. But the water at the bottom of the Mariana Trench has been isolated from the surface for a very long time. Scientists can determine this by measuring dissolved gases, particularly oxygen. Surface water in contact with the atmosphere absorbs oxygen, and photosynthetic plankton produce more. Deep water, cut off from both these sources, gradually loses oxygen as bacteria and other organisms consume it in the process of breaking down organic matter. The water at the bottom of the Challenger Deep has measurable oxygen, which tells us that it's not completely stagnant. There is some slow circulation, bringing slightly fresher water from shallower depths. But oxygen levels are lower than in surface waters, and this affects the types of organisms that can survive there. The trench water also contains dissolved carbon dioxide, which forms carbonic acid when it reacts with water, slightly lowering the pH and making the deep ocean more acidic than surface waters. This deep acidification is different from the ocean acidification caused by humans absorbing carbon dioxide from the atmosphere, which affects primarily surface waters. The natural deep ocean acidity comes from the breakdown of organic matter and the dissolution of carbonate shells over millions of years. It's strong enough that calcium carbonate, the material that makes up seashells and coral skeletons, dissolves in the deepest parts of the ocean, which is why the sediments in the Mariana Trench contain less biogenic carbonate than sediments from shallower depths. Temperature is another crucial factor. The water at the bottom of the trench stays between 1 and 4 degrees Celsius year-round, cold enough to chill you to the bone in minutes if you are somehow exposed to it, but warm enough that it doesn't freeze. Seawater's freezing point is below 0 degrees Celsius because the dissolved salts depress the freezing point, an example of what chemists call a colligative property. At the pressure found in the Challenger Deep, the freezing point drops even further, to about minus 2.6 degrees Celsius. So while the water is cold, it's comfortably above its freezing point given the conditions. This cold temperature affects everything from the rate of chemical reactions to the metabolism of organisms living there. Cold water is denser than warm water, which is why the deepest ocean is filled with water that originated near Earth's poles, where it cooled and sank. This polar water flows along the ocean bottom, moving slowly but inexorably toward the equator, a journey that can take hundreds or thousands of years. The water at the bottom of the Mariana Trench started its journey, perhaps in the North Atlantic or the Antarctic, sank to the abyss, and has been slowly flowing and mixing ever since. Scientists have also found elevated levels of certain noble gases in trench water, particularly helium-3 and xenon. These gases come from the Earth's mantle, released through cracks in the seafloor, or from hydrothermal vents. Their presence indicates ongoing geological activity, the release of primordial gases trapped in Earth's interior since the planet formed more than 4.5 billion years ago. Measuring these gases helps scientists understand the exchange between Earth's interior and the ocean, a process that affects everything from the chemistry of seawater to the global carbon cycle. The pressure at these depths, as we've discussed, exceeds 1,000 atmospheres, and this pressure affects how molecules behave. Water molecules themselves are pushed closer together, increasing the water's density by about 5% compared to surface water. This might not sound like much, but it's enough to matter for organisms trying to maintain neutral buoyancy or for equipment designed to withstand these forces. The pressure also affects chemical equilibria, the balance of reactions between different dissolved substances, subtly shifting which forms of various compounds are most stable. One of the most intriguing aspects of deep trench water is its age. By measuring the decay of radioactive isotopes, particularly carbon-14, scientists can estimate how long water has been isolated from the surface. Some deep ocean water is more than 1,000 years old, and water in the deepest trenches may be older still. This water has circulated through the deep ocean for longer than human civilization has existed, carrying with it a chemical memory of past climate conditions and ocean states. The water at the bottom of the world, then, is a time capsule, a medium that's both the same as surface water in its fundamental composition and profoundly different in its properties and history. It's this water, cold, dark, pressurized and ancient, that organisms must adapt to if they're going to survive in the Hadal Zone. And as we'll see, life has found remarkable ways to do exactly that, turning the challenges of this environment into opportunities and thriving in conditions that seem, by any reasonable standard, impossible for biology. On January 23, 1960, two men climbed into a small metal sphere attached to a large tank of gasoline and began a descent that would take them to the deepest point on Earth. Their names were Jacques Piccard, a Swiss oceanographer and engineer, and Don Walsh, a lieutenant in the United States Navy. Their vehicle was the Trieste, a bathyscaphe designed by Jacques' father, Auguste Piccard, and it represented one of the most audacious feats of engineering and human courage in the history of exploration. The Trieste worked on a principle similar to a balloon, but inverted, where a balloon uses a lightweight gas, helium or hot air, to achieve buoyancy and rise through the atmosphere. The Trieste used gasoline, which is lighter than water and incompressible, to provide buoyancy in the ocean. The gasoline was contained in a large tank above the pressure sphere where the crew sat. To descend, the bathyscaphe carried ballast, heavy iron pellets that could be released electromagnetically when it was time to return to the surface. The crew compartment itself was a steel sphere, with walls more than 12 centimeters thick, barely large enough for two people to sit in cramped positions, with a single small window made of acrylic plastic that was 40 centimeters thick to withstand the pressure. The descent took nearly 5 hours, a slow sinking through the water column, as Piccard and Walsh passed through zones of increasing pressure and darkness. They carried lights, but in the deep ocean, those lights revealed only a small volume of water around them, teeming with particles and occasional organisms. They had instruments to measure depth, temperature, and other parameters, and they had a communication system that allowed them to send simple messages to the surface ship using underwater sound signals, though conversations were impossible. At a depth of about 9,000 meters, they heard a loud crack, a sound that must have sent a spike of adrenaline through both men's bodies. One of the acrylic windows in the entrance tunnel, not the main viewing port but a secondary window, had developed a crack under the immense pressure. They faced a decision. They could abort the dive, drop the ballast, and ascend to safety, or they could continue, trusting that the crack wouldn't propagate, that the window would hold. They chose to continue, a decision that speaks to the particular kind of courage required of explorers, the willingness to push into the unknown even when the risks are tangible and immediate. They reached the bottom of the Challenger Deep at 1:06 p.m. local time, marking their depth as 10,116 meters, though subsequent measurements have revised this to slightly less, around 10,911 meters. They spent only 20 minutes on the bottom, time enough to make a few observations through their tiny porthole. Piccard reported seeing a flatfish, a creature that looked like a sole or flounder, resting on the sea floor. This observation was controversial because flatfish are typically associated with much shallower waters, and some scientists questioned whether what Piccard saw was really a fish or perhaps a sea cucumber or some other organism. Regardless, the fact that they saw any life at all was revolutionary. It definitively disproved the idea that the deepest ocean was lifeless. Then they began their ascent, a process that took about 3 hours and 15 minutes, faster than the descent because they weren't controlling their rate of rise, but simply floating upward after dropping all their ballast. They surfaced safely, and their achievement made headlines around the world. They had gone where no human had ever been, to the lowest point on Earth's surface, and returned to tell about it. For more than 50 years after that dive, no one else attempted to reach the Challenger deep. The Trieste was retired, and while other deep-sea submersibles were built, none were rated for the extreme depth of the Hadal zone. The technology existed, but the cost and difficulty of such dives meant that they weren't undertaken often. The deep ocean remained less visited than the Moon, where 12 astronauts walked between 1969 and 1972. Then, in March 2012, filmmaker James Cameron, director of Titanic and Avatar, made a solo descent to the Challenger deep in a submersible called the Deep Sea Challenger. Cameron's dive was much shorter than Pickard and Walsh's historic journey, just a few hours on the bottom, but he carried high-definition cameras and sampling equipment, bringing back footage and specimens that gave scientists and the public a new window into this alien realm. Cameron described the experience as entering another world, a landscape of ooze and strange creatures lit only by his submersible's lights. More recently, beginning in 2019, explorer Victor Vescovo has made multiple dives to the Challenger Deep and to other deep points in ocean trenches around the world, part of a project called the 5 Deeps Expedition. Vescovo's submersible, the DSV limiting factor, is designed for repeat dives to full ocean depth, and he's made more dives to the Challenger Deep than anyone else, slowly accumulating data and observations that are helping scientists understand this extreme environment better. Each of these expeditions has revealed something new. Cameron found new species of amphipods, shrimp-like crustaceans that thrive at extreme depths. Vescovo discovered plastic bags and candy wrappers on the seafloor, sobering evidence of human pollution reaching even the most remote places on Earth. Scientists analysing the samples and data from these dives continue to make discoveries about the biology, geology, and chemistry of the Hadal zone. But despite these achievements, the total time humans have spent at the bottom of the Challenger Deep adds up to less than a day. We've visited, but we haven't stayed. We've glimpsed, but we haven't truly explored. The deep ocean remains largely unknown, a frontier that's technically accessible, but practically difficult to study. And the Mariana Trench, despite being the most famous of the deep trenches, keeps most of its secrets still. When Jacques Piccard and Don Walsh reached the bottom of the Challenger Deep in 1960 and reported seeing life, it shocked the scientific community. The prevailing wisdom held that life at such depth should be impossible, that the crushing pressure, the complete darkness, the near-freezing temperatures, and the scarcity of food would create conditions fundamentally incompatible with biology. And yet life was there. In the decades since that first dive, as submersibles, remotely operated vehicles, and baited camera systems have allowed us to observe and sample the Hadal zone more thoroughly, we've discovered that the deep trenches aren't barren deserts, but ecosystems. Strange and sparse compared to coral reefs or rainforests, but ecosystems nonetheless, with their own species, their own food webs, and their own unique adaptations. Perhaps the most abundant visible creatures in the Mariana Trench are amphipods, small crustaceans related to the beach hoppers you might see under driftwood on a sandy shore, but adapted in extraordinary ways to life in the abyss. While surface amphipods are typically a few millimeters long, Hadal amphipods can grow to impressive sizes, with some species exceeding 30 centimeters in length. They're often translucent or pale-colored, since camouflage pigments serve no purpose in the darkness, and they have large, powerful legs for scuttling across the seafloor. These amphipods are scavengers, feeding on whatever organic matter drifts down from the surface world or washing across the trench floor in weak currents. They're remarkably efficient at finding food, responding to chemical cues, the scent of decay that spreads through the water. Scientists have used baited camera systems to study them, lowering containers of fish or other bait attached to cameras and lights, and watching as amphipods swarm to the meal, sometimes arriving in their hundreds or thousands within hours. It's a behaviour that makes sense in an environment where food is scarce. You can't afford to ignore a potential meal just because it's not convenient. The other abundant fish-like creatures in the trench are snailfish, small tadpole-shaped fish with soft scaleless bodies and delicate bones that are more cartilaginous than calcified. Snailfish have been found at depths exceeding 8,000 meters, making them the deepest living fish known to science. They glide slowly over the seafloor, using chemical sensors to detect prey, which primarily consists of amphipods and other small crustaceans. Their bodies are adapted in fascinating ways to handle the pressure, with special proteins that prevent their cells from collapsing and a reduced skeleton that doesn't need to be as strong as that of fish in shallower waters where swimming speed and predator avoidance are more important. Then there are the xenophyophores, single-celled organisms that grow to extraordinary sizes, sometimes reaching 10 centimeters or more in diameter. They're related to amoebas, but they build elaborate shells or tests from sediment particles and organic matter, creating structures that look like intricate sculptures. These creatures are incredibly abundant in some parts of the deep ocean, covering the seafloor like a strange carpet, and they play an important role in the ecosystem by processing sediment and providing habitat for smaller organisms. Sea cucumbers, relatives of starfish and sea urchins, are also common in the trenches. They creep slowly across the seafloor, their bodies soft and flexible, ingesting sediment and extracting whatever organic matter it contains. It's a humble existence, eating mud for a living, but in the deep ocean, where energy is scarce, this strategy works. Sea cucumbers are some of the most abundant animals by weight in the Hadal zone. Their slow, patient processing of sediment, a crucial part of the nutrient cycle. Scientists have also discovered various species of polychaete worms, relatives of earthworms, but adapted to marine life, burrowing through the sediments or building tubes attached to rocks. These worms vary in size from tiny thread-like species barely visible to the naked eye to larger forms several centimeters long. They feed on bacteria, detritus, and in some cases on other small animals, occupying various niches in the trench food web. Microbial mats, dense communities of bacteria and archaea, cover portions of the seafloor in some areas, particularly near hydrothermal vents or cold seeps, where chemicals seeping from the sediments provide energy for chemosynthesis. These mats can be white, yellow, or rust-colored, depending on the species involved, and they represent a different kind of primary production, one that doesn't depend on sunlight but on Earth's internal chemistry. One of the most surprising discoveries in recent years has been the sheer diversity of life in the trenches. Each expedition that samples the Hadal zone finds new species, organisms that exist nowhere else on Earth. The trenches are isolated from one another, separated by ridges and shallower seafloor that the highly pressure-adapted species can't cross. So each trench system has developed its own unique fauna over millions of years of evolution. The Mariana Trench, the Tonga Trench, the Kermadec Trench, each has species found nowhere else, examples of what biologists call endemism. This diversity challenges our understanding of what limits life. For decades, scientists thought that life's depth limit would be determined by pressure, that there would be some threshold beyond which proteins couldn't fold properly or cell membranes couldn't maintain their integrity. But organisms in the Hadal zone have evolved biochemical solutions to these problems, solutions that are only now being studied in detail. The trenches, in other words, aren't at the limit of life. They're thriving within a harsh environment that life has successfully colonized, adapted to, and diversified within. The unexpected garden at the bottom of the Mariana Trench reminds us that life is more resilient, more creative in its solutions, and more widespread than we often imagine. The conditions there seem impossible, yet organisms have made them possible. The question isn't whether life can exist in extreme environments, It's what the actual limits are and whether we've found them yet. In the surface ocean, life revolves around the sun. Phytoplankton capture solar energy through photosynthesis, tiny algae converting carbon dioxide and water into organic matter using light as fuel. These microscopic plants form the base of a food web that extends upward to progressively larger animals. Zooplankton grazing on phytoplankton, small fish eating zooplankton, larger fish eating smaller fish, and so on up to the apex. Predators like sharks and tuna. It's a system that ultimately depends on light, and when you descend below the sunlight zone past the depth where photosynthesis is possible, you enter a realm where energy must come from elsewhere. In the Mariana Trench, in the complete darkness of the Hydrothermal zone, there's no photosynthesis. Yet life exists, which means there must be a source of energy, a way for organisms to acquire the calories they need to power their metabolism. The primary source, it turns out, is marine snow, a term that refers to the constant rain of organic particles that drifts down from the surface ocean toward the sea floor, a slow-motion blizzard that never stops. Marine snow consists of many things: dead phytoplankton, zooplankton fecal pellets, bits of larger organisms, molted exoskeletons, and aggregates of organic matter held together by mucus secreted by various marine creatures. These particles are small, typically less than a few millimeters across, and they sink slowly, sometimes taking weeks or months to fall from the surface to the deep sea floor. During this descent, they're colonized by bacteria, gradually decomposing, so that by the time they reach the Hydrothermal zone, only the most refractory organic matter remains, the compounds that are hardest to break down. Despite this extensive decomposition, enough organic matter reaches the trench floor to support life. Scientists estimate that perhaps 1 to 2% of the organic matter produced in surface waters eventually makes it to the deepest parts of the ocean. It doesn't sound like much, but spread over the vast area of the ocean floor and accumulated over time, it adds up. The seafloor in the trenches is covered with a layer of sediment rich in organic matter, and organisms that can process this sediment, eating it and digesting the organic content, can make a living. But marine snow isn't the only source of food. Occasionally, much larger packages of organic matter arrive at the trench floor. When a large fish, a whale, or even a piece of driftwood sinks, it represents a bonanza of food, enough to support a community of scavengers for months or years. These are called foodfalls, and they create temporary oases of abundance in an otherwise sparse environment. The amphipods and other scavengers in the trench are exquisitely sensitive to the chemical signals of decay, and they can converge on a foodfall from distances of hundreds of meters or more, guided by the diffusion of organic molecules through the water. Whale falls are particularly important. When a large whale dies and sinks to the deep sea floor, its body, which might weigh tens of tons, provides an enormous amount of food. Scientists studying whalefall communities have found them to be remarkably diverse, supporting not just scavengers that eat the soft tissue, but also specialized organisms that consume the lipid-rich bones over decades as they slowly decompose. Some species of polychaete worms have evolved to bore into whale bones, partnering with symbiotic bacteria that can break down the fats inside. These whalefall communities can persist for 50 to 100 years, islands of abundance in the deep. There's also another source of energy in the deep ocean, one that doesn't depend on sunlight, even indirectly. This is chemosynthesis, a process where bacteria and archaea use the chemical energy in reduced compounds, such as hydrogen sulfide, methane, or ammonia, to produce organic matter. These reduced compounds come from Earth's interior, seeping out through hydrothermal vents or cold seeps, and the chemosynthetic microbes that oxidize them form the base of food webs that are completely independent of photosynthesis. Hydrothermal vents are dramatic features. places where seawater that has percolated through cracks in the oceanic crust is heated by magma below and then erupts back into the ocean, carrying dissolved minerals and gases. The water can be superheated, exceeding 400 degrees Celsius, though it doesn't boil due to the pressure. When this hot water mixes with the cold seawater, the minerals precipitate, creating chimney-like structures that billow black or white smoke, the black coming from iron sulfide, the white from silicon dioxide and calcium sulfate. While no hydrothermal vents have been discovered yet in the Mariana Trench itself, there are vents in the nearby Mariana Back Arc, a region of volcanic activity associated with the subduction zone. It's entirely possible that vents exist in the trench as well, hidden in areas that haven't been explored yet. If they do, they would support their own unique communities of organisms, including bacteria and archaea that oxidize hydrogen sulfide, and animals like tube worms and vent crabs that either farm these bacteria or feed on them directly. Cold seeps are more subtle than hydrothermal vents, but potentially more widespread. These occur where methane and other hydrocarbons seep from sediments, often from pockets of gas trapped beneath the sea floor. Chemosynthetic bacteria oxidize the methane, and animals like clams and mussels with symbiotic bacteria in their tissues thrive in these environments. Cold seeps have been found in many deep-sea environments, and they likely exist in the Mariana Trench as well, another potential source of energy for life. The food web in the Mariana Trench, then, is complex. At the base are the bacteria and archaea that decompose organic matter and, in some places, perform chemosynthesis. These microbes are eaten by small animals like nematodes and copepods, which in turn are eaten by larger animals like amphipods and polychaete worms. The amphipods and worms are eaten by snailfish, and so on. It's a food web with fewer levels than in the surface ocean, a consequence of the limited energy available. But it's a food web nonetheless, a network of who eats whom that connects even the deepest parts of the ocean to the global ecosystem. And it's a food web that operates in slow motion. Metabolism at these cold temperatures and under these conditions of food scarcity is slow. Animals grow slowly, reproduce slowly, and live a long time. Some deep-sea organisms are thought to live for decades or even centuries. Their slow pace of life, a consequence of and an adaptation to their environment. In the darkness with limited food, patience is a survival strategy. Imagine trying to survive at the bottom of the Mariana Trench without any special adaptations. The pressure alone would be immediately fatal, compressing any air-filled space in your body, squeezing the gas out of your lungs and blood, crushing your chest cavity. Even if you could somehow survive the initial compression, the cold would kill you within minutes, your body temperature plummeting as heat flowed into the surrounding water. And yet fish, crustaceans, and countless other organisms live at these depths, moving and feeding and reproducing as if the conditions were perfectly normal. How do they do it? The key is that these organisms don't have any gas-filled spaces. Surface-dwelling fish have swim bladders, gas-filled organs that provide buoyancy, allowing them to hover at a particular depth without expending energy swimming. But gas is compressible, and a swim bladder that works at the surface would collapse into a tiny, useless volume at the pressure of the Mariana Trench. So, deep-sea fish either lack swim bladders entirely or have evolved other ways of achieving buoyancy, such as storing lipids, which are less dense than water and incompressible. The Hadal snailfish, for example, have soft, gelatinous bodies with high water content and no swim bladder. They're slightly denser than seawater and sink slowly when not swimming, but their large pectoral fins allow them to glide efficiently, and they don't need to maintain a constant depth the way a surface fish with a swim bladder does. Their bones are reduced and cartilaginous, which makes sense because in the Hadal zone, there's no need for the strong calcified skeleton required for fast swimming or predator avoidance in shallower waters. At the cellular level, Deep-sea organisms face a different challenge. Pressure tends to disrupt the structure of proteins and cell membranes. Proteins are large, complex molecules that fold into specific three-dimensional shapes, and these shapes are crucial to their function. Pressure can change these shapes, deforming proteins and potentially preventing them from doing their jobs. Cell membranes, which are made of lipids arranged in a double layer, can also be affected, becoming less fluid and more rigid under pressure. To counter these effects, deep-sea organisms produce special molecules called piezolytes or osmolytes. One of the most important is trimethylamine oxide, or TMAO, a small organic compound that helps stabilize proteins and membranes under high pressure. TMAO is found in high concentrations in deep-sea fish, amphipods, and other hadal organisms. Interestingly, TMAO is also the compound that gives fish their characteristic smell when they start to decompose, which is why deep-sea fish brought to the surface often have a particularly strong odor. Scientists have studied how TMAO works at the molecular level, and it's quite elegant. The molecule interacts with water molecules in a way that counteracts the pressure-induced perturbations to protein structure. It's as if TMAO creates a protective cushion around proteins, allowing them to maintain their proper shape and function despite the crushing forces. The concentration of TMAO in an organism's tissues correlates with the depth at which it lives. The deeper the animal's habitat, the more TMAO it produces. There's a limit to this, though. As depth increases, so does the required concentration of TMAO. And eventually, you reach a point where the TMAO concentration becomes so high that it starts to interfere with other cellular processes. Some scientists believe this might represent the absolute depth limit for fish, the point beyond which no amount of TMAO can compensate for the pressure. Calculations suggest this limit might be around 8,200 to 8,500 meters, which is intriguing because the deepest fish ever recorded, a hadal snailfish, was found at about 8,178 meters. No fish have been confirmed below about 8,400 meters, even though the trenches go much deeper. Perhaps we're seeing the actual physiological limit of what fish biochemistry can achieve. But even if fish can't survive in the deepest parts of the trenches, other organisms can. Amphipods, with their arthropod body plan and different biochemistry, have been found at the bottom of the Challenger Deep. They must have their own adaptations, their own molecular tricks for dealing with pressure, though these are less well studied than those of fish. Another important adaptation in deep-sea organisms is the structure of their cell membranes. At high pressure, membranes tend to become more ordered, more rigid, which can impair their function. Deep-sea organisms compensate by adjusting the lipid composition of their membranes, incorporating more unsaturated fatty acids, which have kinks in their molecular structure that prevent tight packing. This keeps the membranes fluid and functional, even under pressure. The metabolic rate of deep-sea organisms is also adapted to their environment. Metabolism tends to slow down at cold temperatures, and this is true for hadal organisms as well. They have a low metabolic rate, which means they need less food and produce less waste. But it also means they grow slowly and have long generation times. This slow pace of life is well suited to an environment where food is scarce and unpredictable. One of the fascinating aspects of these adaptations is that they're not unique to a single lineage. Many different groups of organisms have independently evolved similar solutions to the problem of living at extreme depth. Fish, crustaceans, worms all use TMAO or similar osmolytes. All have adjusted their membrane lipid composition. This convergent evolution suggests that there are only so many ways to solve the pressure problem, and life has found them repeatedly. The organisms living in the Mariana Trench, then, aren't just surviving despite the pressure. They're thriving because of a suite of biochemical and physiological adaptations that make the extreme conditions not just tolerable, but normal. Their bodies are built for pressure, optimized for an environment that seems alien to us, but is home to them. And in studying these adaptations, scientists gain insights not just into deep-sea biology, but into the fundamental principles of biochemistry, the limits of life, and the possibilities for biology in other extreme environments, whether in subsurface oceans on distant moons or in conditions we haven't even imagined yet. If you could somehow visit the Mariana Trench in person, protected by some miraculous technology that let you walk the seafloor as easily as you might walk through a terrestrial forest, the creatures you'd encounter would seem utterly alien. Forms of life shaped by millions of years of evolution in an environment so different from the surface world that they've taken on appearances and behaviours unlike anything in more familiar habitats. Let's meet some of these organisms, the strangest creatures on Earth, inhabitants of the deepest places in the ocean. First, imagine encountering a Hydrothermal amphipod, but not the small, shrimp-like crustaceans you might be familiar with from beaches or shallow waters. Hydrothermal amphipods can grow to astonishing sizes, with some species exceeding 30 centimeters in length, nearly a foot long. They're often pale or translucent, their bodies lacking pigments, because color serves no purpose in the darkness. Their exoskeletons are hard enough to protect them, but also flexible, allowing them to move efficiently across the soft sediment of the trench floor. These amphipods are scavengers, equipped with powerful mouthparts for tearing flesh and digestive systems that can process a wide variety of organic matter. They're remarkably mobile for creatures of their environment, capable of covering significant distances in search of food. When scientists deploy baited camera systems in the trenches, amphipods often appear within hours, swarming over the bait in their hundreds, a writhing mass of pale bodies that strip the food to nothing in a day or two. It's a reminder that scarcity breeds efficiency. In an environment where meals are rare, you can't afford to be slow or picky. Then there are the Hadal snailfish, arguably some of the most remarkable vertebrates on Earth. These fish are small, typically less than 30 centimeters long, with tadpole-like bodies and large wing-like pectoral fins that they use to glide slowly over the seafloor. Their skin is loose and gelatinous, almost translucent, and they have no scales. Their skulls are incomplete, with spaces between bones that would be solidly fused in shallow water fish. This might seem like a weakness, but at extreme depth, it's an adaptation, reducing the need for heavy skeletal structures and allowing the fish's body to be more compliant, more easily equilibrated with the surrounding pressure. Hadal snailfish have tiny eyes, often reduced to the point of being barely functional, because vision is of limited use in the darkness. Instead, they rely on other senses, particularly chemoreception and mechanoreception, detecting chemical cues and vibrations in the water to find prey. They feed primarily on amphipods and other small invertebrates, swimming slowly above the seafloor and striking when they detect something edible. Their metabolism is slow, matching the cold temperature and scarcity of food, and they likely live for many years, decades perhaps, slowly growing in the darkness. Among the most bizarre creatures in the trenches are the xenophyrophores, single-celled organisms that can grow to remarkable sizes. To call them single-celled seems almost misleading because they can be 10 centimeters across or more, easily visible to the naked eye, larger than many multicellular animals. They're related to amoebas, members of a group called Foraminifera, but they've evolved to gigantic proportions and complex structures. Xenophyrophores build tests or shells from sediment particles, organic matter, and even the skeletons of other organisms, cementing them together with organic secretions to create elaborate branching structures that look more like sculptures than living things. These creatures are found on the seafloor in many deep-sea habitats, and they're particularly abundant in some parts of the Mariana Trench. They're detritivores, processing sediment and extracting organic matter, and they also provide habitat for smaller organisms. They're complex tests, creating spaces where bacteria, nematodes, and other tiny creatures can live. Despite their size and abundance, xenophyrophores remain poorly understood because they're so fragile that bringing them to the surface intact is nearly impossible. They tend to collapse or disintegrate when removed from their high-pressure environment, which makes studying them difficult. Sea cucumbers in the Hadal zone are also worth mentioning. These relatives of starfish and sea urchins creep across the seafloor, their soft, sausage-shaped bodies muscular and flexible. They ingest sediment at one end and excrete processed sediment at the other, extracting whatever organic matter and bacteria the sediment contains. It's a humble existence, but sea cucumbers are incredibly important in the deep-sea ecosystem. They're among the most abundant animals by biomass in the trenches, and their processing of sediment affects nutrient cycling, mixing surface and deeper layers of sediment and distributing organic matter. Some deep-sea sea cucumbers have evolved remarkable features. Species like Enypniastes, sometimes called the headless chicken monster because of its bizarre appearance, have webbed swimming structures and can move through the water column, not just crawl across the bottom. Others have elongated tentacles around their mouths that they use to sweep up sediment particles or capture small organisms. Their diversity in form and feeding strategy is a testament to the evolutionary creativity that deep-sea environments have fostered. Polychaeta worms, segmented worms that are relatives of earthworms, come in an astonishing variety in the deep trenches. Some are predatory, with fearsome jaws that they use to capture other worms or small crustaceans. Others are filter feeders, building tubes from mucus and sediment and extending feathery gills into the water to capture particles. Still others burrow through the sediment, leaving tiny trails as they move. Each species occupies a slightly different niche, feeding on different things, living at different depths in the sediment, reproducing at different times or in different ways. What unites all these creatures is that they're specialized, adapted over countless generations to the specific conditions of the Hadal zone. They're not primitive or simple, they're highly evolved for their environment, with biochemistries and anatomies that solve the problems of extreme depth, cold, darkness, and food scarcity. They're strange to us because they're so different from the organisms we encounter in our daily lives, but in their own context, they're perfectly suited to their world. They're reminders that life doesn't have a single form, a single way of being, but rather an almost infinite capacity to adapt, to find solutions, to make a home in environments that seem, from our perspective, utterly inhospitable. In the complete darkness of the Mariana Trench, you might think that light would be irrelevant, a sense that evolution would have discarded long ago because it serves no purpose where no light exists. And yet, many deep-sea organisms produce their own light, a phenomenon called bioluminescence. And this light plays crucial roles in how they communicate, find prey, avoid predators, and reproduce. The paradox is that in a world without sunlight, organisms have evolved to create their own illumination, turning darkness into a different kind of visual landscape, one punctuated by flashes, glows, and patterns of living light. Bioluminescence in the ocean is created through a chemical reaction, typically involving a light-emitting molecule called luciferin and an enzyme called luciferase. When luciferin is oxidized in the presence of luciferase, it releases energy in the form of light, usually blue or green, because these wavelengths travel farthest in seawater. Different organisms use different variants of luciferin and luciferase, suggesting that bioluminescence has evolved independently multiple times in the history of life, a convergent solution to the challenges and opportunities of living in darkness. In the mesopelagic zone, the twilight zone where faint sunlight still penetrates, bioluminescence is incredibly common. Some estimates suggest that more than 90% of the organisms in this zone are capable of producing light. They use it for counter-illumination, a camouflage technique where light organs on the underside of an animal match the faint downwelling light from above, making the animal effectively invisible to predators looking up from below. They use it for communication, flashing specific patterns to identify themselves, to potential mates, or to coordinate with members of their own species. They use it for predation, with some fish sporting bioluminescent lures to attract prey close enough to strike. In the bathypelagic and abyssal zones, where no sunlight penetrates at all, bioluminescence is less common but still important. Deep-sea anglerfish, those famous denizens of the abyss, with their enormous mouths and fearsome teeth, use a bioluminescent lure dangling in front of their faces. The lure is actually a modified dorsal fin spine that hosts bioluminescent bacteria, and the bacteria produce a steady glow that attracts smaller fish or invertebrates. When prey comes to investigate the light, the anglerfish strikes, its mouth opening with astonishing speed to engulf the unsuspecting victim. Many deep-sea shrimp and squid produce clouds of bioluminescent particles when threatened, the underwater equivalent of a smokescreen. The burst of light confuses or startles the predator, and while the predator is distracted, the prey escapes into the darkness. Some squid can even direct their bioluminescent emissions, creating patterns or flashes that might communicate information or serve as warnings to predators that they're toxic or unpalatable. In the Hadal zone, bioluminescence is less well studied, simply because the extreme depths make observation difficult. But we know that some amphipods from the Mariana Trench are bioluminescent, producing light through photophores, specialized light-producing organs. The purpose of this light at such extreme depths isn't entirely clear. It might be used for communication, though what messages amphipods need to send in the darkness is a question that awaits more research. It might be used to startle predators. It might even be a vestigial trait, retained from shallower-dwelling ancestors, even though it no longer serves a clear function, though this seems unlikely given the energetic cost of producing light. One of the most intriguing possibilities is that bioluminescence in the Hadal zone is used for reproduction, a way for individuals to find one another in the vast darkness. In the deep sea, finding a mate can be extraordinarily difficult. Population densities are low, and the three-dimensional space of the ocean is enormous. Some deep-sea fish have evolved extreme sexual dimorphism, with tiny males that permanently attach to females, fusing their bodies and sharing a circulatory system, a strategy that ensures that when the female is ready to reproduce, a male is always available. Other species might use bioluminescent signals, specific flash patterns or intensities, to identify themselves to potential mates and coordinate reproduction. The chemistry of bioluminescence is also being studied for practical applications. Luciferase enzymes are used in research laboratories as reporters, molecules that indicate when a particular gene is active or a particular process is occurring. Bioluminescent bacteria and proteins have been engineered into organisms to make them glow, a technique used in everything from studying cancer cells to creating glow-in-the-dark plants. Understanding how deep-sea organisms produce light so efficiently, with so little waste heat, could inspire new technologies for lighting and imaging. What's particularly fascinating about bioluminescence in the deep ocean is how it represents a completely different visual ecology from what we experience on land. On the surface, during the day, the world is bathed in sunlight, a constant diffuse illumination that allows vision across long distances. In the deep sea, the world is dark, but not invisibly so. It's a darkness pierced by occasional flashes and glows, each one a signal or a lure or a warning, each one carrying information. Organisms there have evolved to see these brief emissions, to interpret them, to respond. Their eyes, while often reduced in size compared to surface organisms, are sensitive to very low light levels, capable of detecting single photons. The deep ocean's light show is invisible to us unless we bring cameras and lights, but for the organisms that live there, it's their reality, the visual landscape they navigate every day. Bioluminescence turns the darkness into something less oppressive, less absolute. It's a reminder that even in the most extreme environments, life finds ways to communicate, to interact, to create beauty of a sort, patterns of light in the depths that no human saw until very recently, and that, even now, we're only beginning to understand. When we think about the Mariana Trench, we often focus on the visible creatures, the amphipods and snailfish and sea cucumbers that cameras can capture and that fit our intuitions about what an animal should be. But the truth is that the majority of life in the trench, as in most ecosystems on Earth, is invisible to the naked eye. These are the microorganisms, bacteria and archaea, that exist in unimaginable numbers in the sediments and water of the Hadal zone. And they're not just passengers or decomposers, but active participants in the ecosystem, driving chemical cycles and providing the foundation for much of the food web. Every gram of sediment from the Mariana Trench contains millions, or even billions, of microbial cells. These aren't dead or dormant organisms, but living, metabolizing cells that reproduce, adapt, and evolve. They're incredibly diverse, with different species specialized to use different energy sources, to tolerate different conditions, to occupy different chemical niches within the sediment. Scientists who study these communities use genetic sequencing to identify the species present, and they consistently find that the majority of species, often more than 90%, are previously unknown to science. Organisms with no names, no classification, no close relatives in existing databases. These bacteria and archaea are adapted to extreme conditions in ways that challenge our understanding of life's limits. Many are piezophiles, organisms that not only tolerate high pressure, but require it for optimal growth. When scientists bring sediment samples to the surface and try to culture the microbes in the laboratory at normal atmospheric pressure, most of them don't grow or grow very poorly. They need the pressure. Their enzymes and membranes and cellular processes are tuned to function best under hundreds of atmospheres of force. This makes studying them difficult because it requires specialized equipment that can maintain high pressure, but it also makes them fascinating because it shows how adaptable life can be. The metabolic diversity of these microbes is astonishing. Some are heterotrophs, consuming organic matter and breaking it down through fermentation or respiration, processes similar to what happens in our own bodies or in the soil of a forest. Others are chemolith autotrophs, a mouthful of a term that means they can build organic matter from carbon dioxide using energy from inorganic chemical reactions. These organisms oxidize reduced compounds like hydrogen sulfide, methane, ammonia, or even iron and manganese. Reactions that release energy that the microbes capture and use to fuel their metabolism. In areas of the trench floor where methane seeps from the sediments, you find communities of methanotrophic bacteria, organisms that consume methane as their primary energy source. These bacteria are crucial for regulating the flux of methane from the seafloor into the water column and potentially into the atmosphere. Methane is a potent greenhouse gas, much more effective at trapping heat than carbon dioxide, so the activity of these bacteria has implications for Earth's climate, though the exact magnitude of this effect is still being studied. There are also archaea in the trench sediments, members of a domain of life that's distinct from bacteria and eukaryotes. Archaea are often found in extreme environments, from hot springs to salt lakes to the deep subsurface, and the Hadal zone is no exception. Some archaea in the Mariana Trench are methanogens, organisms that produce methane as a byproduct of their metabolism, essentially doing the opposite of the methanotrophic bacteria. Others are ammonia-oxidizing archaea, which play a key role in the nitrogen cycle, converting ammonia into nitrite, a form of nitrogen that other organisms can use. The genetic diversity of these microbial communities is a treasure trove for science. Microbes have small genomes compared to larger organisms, but they evolve quickly and exchange genetic material through horizontal gene transfer, so the diversity of genes in a microbial community can be enormous. Studying these genes reveals enzymes and metabolic pathways that might have practical applications, from breaking down pollutants to synthesizing pharmaceuticals to catalyzing industrial reactions. There's also the basic scientific interest in understanding how these organisms work, what biochemical tricks they use to survive in extreme conditions. Viruses are also present in the Hadal zone, though they've been less studied. Viruses infect bacteria and archaea, inserting their genetic material and hijacking the host cell's machinery to produce more viruses. When the host cell bursts, it releases new viruses and also releases organic matter, nutrients that other microbes can use. Viral infection is a major source of mortality for bacteria in many marine environments, and the same is likely true in the trenches. The viruses themselves are incredibly diverse, with each one typically specialized to infect a narrow range of hosts. One of the challenges in studying deep-sea microbial communities is that we can't see most of what they're doing in real time. We can sequence their DNA and infer what metabolic capabilities they have, but inferring isn't the same as observing. We can take sediment samples and measure the concentrations of various chemicals, then make educated guesses about which microbes are active and what they're doing. But these are snapshots, moments frozen in time, not the dynamic processes themselves. Recent advances in technology are starting to change this. Scientists are deploying autonomous landers equipped with sensors that can measure oxygen, pH, and other chemical parameters continuously over weeks or months, building up a picture of how the microbial community responds to changes in food availability, temperature, or other environmental factors. They're also using techniques like stable isotope probing, where they add compounds labeled with heavy isotopes and then track where those isotopes end up, which tells them which organisms are consuming which compounds. The invisible majority in the Mariana Trench, these countless microbes, are the foundation of the ecosystem. They break down organic matter, recycle nutrients, produce and consume gases, and provide food for larger organisms. Without them, the Hadal zone would be lifeless. The organic matter that drifts down from the surface, accumulating endlessly without being processed. With them, the trench is a living system, dynamic and complex. A reminder that ecosystems aren't defined by the charismatic megafauna we can see, but by the intricate web of relationships, visible and invisible, that connect all organisms to one another and to their environment. The ocean is not silent. Beneath the surface, there's a constant background of sound, the rumble of breaking waves at the surface, the clicks and whistles of dolphins, the haunting songs of whales, the grinding of icebergs, and in the deep sea, the low-frequency murmur of geological processes and the occasional sharp crack of an earthquake. Sound travels well in water, much better than in air, and for marine organisms, hearing is often more important than vision for navigating, finding food, avoiding predators, and communicating. In the Mariana Trench, where light cannot penetrate, sound becomes even more crucial. Scientists use hydrophones, underwater microphones, to listen to the trench, recording the acoustic landscape to learn about everything from seismic activity to biological behavior. What they've heard is both fascinating and, at times, mysterious, a soundscape that includes the expected and the unexplained. The most consistent sound from the trench is the deep rumble of tectonic activity. The Mariana Trench sits at a subduction zone where the Pacific Plate is descending beneath the Philippine Sea Plate, and this process is anything but quiet. Earthquakes occur regularly as stress builds up and is suddenly released along the boundary between the plates. These earthquakes range from tiny tremors, barely detectable, even with sensitive instruments, to major events that can generate tsunamis and be felt hundreds of kilometers away. The sound of an earthquake is a low-frequency roar, a sudden increase in acoustic energy that propagates through the water and the seafloor. By placing hydrophones at different locations, scientists can triangulate the source of earthquakes, determining their location and magnitude. This helps build a picture of where seismic activity is concentrated and how stress is distributed along the subduction zone, information that's crucial for understanding earthquake hazards in the region. But earthquakes aren't the only geological sounds. There are also the groans and creaks of the seafloor itself as it deforms, the occasional rumble of an underwater landslide, and potentially the sounds of hydrothermal vents if they exist in the trench, though none have been definitively identified there yet. Hydrothermal vents are noisy features when they're active, the hot water erupting from the seafloor, creating turbulence and acoustic emissions that can be detected from a distance. Then there are the biological sounds. Whales produce some of the loudest sounds in the ocean, their songs and calls travelling for hundreds or even thousands of kilometres. While whales don't dive to the depths of the Mariana Trench, their sounds certainly do, penetrating into the Hadal zone and creating an acoustic backdrop that the organisms living there must be exposed to. Whether deep-sea organisms can hear these sounds, and whether they respond to them in any way, is an open question. Some deep-sea fish and crustaceans are known to produce sounds, typically by stridulation, rubbing body parts together, or by snapping specialized appendages. Snapping shrimp, for example, produce a loud crack by rapidly closing a specialized claw, creating a cavitation bubble that collapses with a sound that can stun small prey. It's not known whether hadal amphipods or other creatures in the Mariana Trench use sound for communication or predation, but it's possible, and hydrophone recordings from the trench might eventually reveal these behaviors. Perhaps the most intriguing sounds from the deep ocean are the ones we can't explain. Over the years, oceanographers have recorded various mysterious, low-frequency sounds, some of which have gained fame because of their eerie, otherworldly quality. The most famous is probably the bloop, a powerful low-frequency sound detected in 1997 by hydrophones in the South Pacific. The bloop was loud enough to be heard by sensors more than 5,000 kilometers apart, and its frequency profile was consistent with a biological source, leading to speculation about giant unknown sea creatures. Later analysis suggested that the bloop was most likely caused by an ice quake, the cracking and fracturing of large icebergs or ice shelves, but the initial mystery captured the public imagination. Other unexplained sounds have been recorded in various parts of the ocean, and while most have eventually been traced to known sources, wind, storms, ships, marine mammals, there remain recordings that don't fit neatly into any category. Could some of these sounds come from the Mariana Trench or similar deep environments? It's possible, though the trench itself is relatively quiet compared to shallower waters, simply because there's less biological activity and fewer organisms overall. One of the challenges in interpreting sounds from the deep ocean is that we have so little baseline data. We don't know what normal should sound like in the Hadal zone because we haven't been listening long enough or comprehensively enough. Deploying hydrophones in the Mariana Trench for extended periods, recording continuously over weeks or months or years, would give scientists a much better sense of the acoustic environment and help identify patterns or anomalies. Sound also provides a way to study the trench without physically visiting it. Acoustic tomography, a technique where sound waves are sent through the ocean and their travel time and distortion are measured, can reveal information about water temperature, salinity, and currents. By setting up an array of acoustic sources and receivers around the trench, scientists could map the water column's properties in 3 dimensions, tracking how water moves through the trench and how it exchanges with the surrounding ocean. The sounds from below, then, are a window into a hidden world, a way of observing and understanding the Mariana Trench that complements visual observation and sampling. They remind us that the ocean is not just a visual space, but an acoustic one. And for the organisms living in darkness, sound is a primary sense, a way of perceiving their environment that we, as primarily visual creatures, often overlook. Listening to the trench, we might hear not just the rumble of geology, but the whispers of life, the subtle communications and movements of organisms that have made this extreme environment their home. It's a sobering thought, but one that we must confront. There is no place on Earth, not even the deepest, most remote corner of the ocean, that remains untouched by human activity. In 2019, explorer Victor Vescovo made multiple dives to the Challenger Deep, and among the things he photographed on the seafloor was a plastic bag and the wrapper from a piece of candy. These items, manufactured thousands of miles away and discarded carelessly, had somehow made their way to the bottom of the world, a journey of more than 36,000 feet through the ocean to rest in what should be one of the last pristine environments on the planet. But it's not just the visible trash that's alarming. Scientists analysing sediment cores and tissue samples from hadal organisms have found microplastics, tiny fragments of plastic less than 5 millimeters in size, and persistent organic pollutants, chemical compounds that don't break down easily and accumulate in fatty tissues. These include polychlorinated biphenyls, or PCBs, which were widely used in industrial applications until they were banned in the 1970s and 1980s because of their toxicity, and polybrominated diphenyl ethers, or PBDEs, which are used as flame retardants. How do these pollutants reach the Mariana Trench? They travel on the same pathway that brings organic matter from the surface, marine snow. Microplastics, which are denser than water, or which have been colonized by bacteria and coated with biofilms, sink slowly through the water column, eventually reaching the sea floor. Along the way, they can be ingested by zooplankton and other organisms, passing into the food web. When larger animals eat contaminated prey, the pollutants accumulate in their tissues, a process called bioaccumulation. Because hadal amphipods and other deep-sea organisms are scavengers, feeding on anything that sinks to the seafloor, they're particularly likely to consume microplastics and contaminated organic matter. Studies of amphipods from the Mariana Trench have found plastic fibers in their stomachs and elevated levels of PCBs and PBDEs in their tissues, concentrations comparable to some of the most polluted coastal areas. This is shocking because the trench is about as far from human population centres and industrial activity as you can get. It demonstrates that pollutants dispersed into the ocean don't stay localised. They spread through currents, through biological uptake and transport, through sinking particles until they're distributed globally, even to the most remote depths. The ecological impacts of this pollution are not yet fully understood. Microplastics can cause physical harm if ingested, blocking digestive tracts or causing internal abrasions. They can also leach chemical additives, plasticizers, stabilizers, pigments that are toxic to organisms. PCBs and other persistent organic pollutants disrupt endocrine systems, interfere with reproduction, and can cause cancer or other diseases. In shallow water and terrestrial ecosystems, these effects have been well documented, but in the hadal zone, where life is already living on the edge, coping with extreme pressure, cold and food scarcity, additional stresses from pollution could have disproportionate impacts. It's not just plastics and industrial chemicals. Radioactive isotopes from nuclear weapons testing in the 1950s and 1960s have also been detected in deep-sea organisms. The fallout from these tests, which occurred primarily in the Pacific Ocean, spread around the world and settled into the ocean. Some of this radioactive material sank to the seafloor, where it was incorporated into sediments and taken up by organisms. Carbon-14, a radioactive isotope of carbon produced by nuclear tests and by natural processes in the atmosphere, has been found in elevated concentrations in deep-sea crustaceans, providing an unexpected marker of the mid-20th century and a tracer of how carbon cycles through the ocean. Mercury, a toxic heavy metal that's released into the environment by coal burning, mining, and other industrial processes, also finds its way into the deep ocean. Mercury is converted by bacteria into methyl mercury, a highly toxic form that bioaccumulates in food webs, reaching high concentrations in predatory fish. Studies have shown that deep-sea fish, including those from near the Mariana Trench, have elevated mercury levels, though whether this poses a risk to the ecosystems or just to any humans who might consume these fish, which is unlikely, is unclear. The presence of pollution in the Mariana Trench is a stark reminder of the interconnectedness of Earth's systems. The ocean is not a series of isolated basins, but a global system where currents, organisms, and chemical compounds move freely. What happens in one part of the ocean, or even on land thousands of miles away, can affect the deepest trenches. It's a humbling realization, and one that should prompt reflection on our responsibilities as a species. But it's not all doom and gloom. The discovery of pollution in the Mariana Trench has galvanized public and scientific attention to the problem of ocean contamination. Efforts to reduce plastic waste, to clean up existing pollution, and to regulate the discharge of harmful chemicals into the environment have gained momentum. The development of biodegradable plastics and alternative materials that don't persist in the environment is an active area of research and innovation. There's also a growing recognition that protecting the deep ocean is just as important as protecting more visible ecosystems like coral reefs and rainforests. The deep sea plays crucial roles in regulating Earth's climate, cycling nutrients, and supporting biodiversity. International agreements and treaties are beginning to address deep-sea conservation, though enforcement and implementation remain challenges. The Mariana Trench, in its pollution as in its biology, holds up a mirror to humanity. It shows us what we've done, the impacts of our industrial civilization reaching even the most remote corners of the planet. But it also reminds us that it's not too late, that understanding leads to awareness, awareness to concern, and concern to action. The fact that we can detect pollution in the trench means we understand the pathways by which it gets there. And if we understand the pathways, we can interrupt them, reduce the flow, begin the long process of restoring even the deepest ocean to something closer to its pristine state. The Mariana Trench exists because of a geological process, subduction, that's also one of the primary drivers of earthquakes and volcanic activity on Earth. The trench sits along the western edge of the Pacific Ocean, part of a vast arc of seismic and volcanic activity known as the Ring of Fire. This ring encircles the Pacific, running from New Zealand up through the Philippines, Japan, and the Aleutian Islands, then down the west coast of North and South America. It's home to about 75% of the world's active volcanoes and is responsible for about 90% of the world's earthquakes. The Mariana Trench is not just a passive feature, but an active participant in these dynamic processes. Earthquakes at subduction zones occur because of the immense forces involved when one tectonic plate descends beneath another. As the Pacific plate slides under the Philippine Sea plate, friction prevents smooth motion. Stress builds up over years or decades as the plates try to move, until the stress exceeds the strength of the rocks, and they suddenly slip, releasing the accumulated energy as seismic waves. This is an earthquake, a sudden rupture along a fault, and it can release energy equivalent to thousands of nuclear weapons. Most earthquakes at the Mariana Trench are relatively small, tremors that might be felt on nearby islands, but that don't cause significant damage. These small earthquakes are actually helpful in a way because they release stress incrementally, preventing it from building up to catastrophic levels. But occasionally, a larger earthquake occurs, a magnitude 7 or 8 event that can be devastating. The Mariana region has experienced several significant earthquakes in recent history, though the trench's remote location and the relatively small populations on nearby islands mean that the impacts are often less severe than earthquakes in more densely populated subduction zones like Japan or Chile. One of the fascinating aspects of subduction zone earthquakes is that they can occur not just at the boundary between the plates, but deep within the descending slab. As the Pacific plate sinks into the mantle, it remains cool and brittle compared to the surrounding hot rock, and it can fracture, generating what are called deep focus earthquakes. These earthquakes can occur at depths of 300 to 700 kilometers, far below the surface, and they're seismically detectable around the world. Deep focus earthquakes are less hazardous than shallow earthquakes because their energy is absorbed by the overlying rock, but they're scientifically interesting because they occur under conditions of temperature and pressure where rock should be too ductile to fracture. The geometry of earthquake locations at the Mariana Trench defines what's called the Wadati-Benioff zone, named after two seismologists who first mapped the pattern. If you plot earthquake locations in cross-section, you see a plane of seismic activity dipping from the trench downward into the mantle, marking the descending Pacific plate. This plane curves gently, following the shape of the plate as it bends and sinks, and it extends to depths of several hundred kilometers. Mapping this zone helps geologists understand the structure of the subduction zone and how the plate behaves as it descends. Earthquakes at subduction zones can also generate tsunamis, large ocean waves that can travel across entire ocean basins and cause devastating damage when they reach shore. Tsunamis are caused by sudden vertical displacement of the seafloor during an earthquake. If the earthquake is large enough and shallow enough, and if it causes significant uplift or subsidence of the seafloor, it can displace a huge volume of water, which then propagates outward as a tsunami. In the open ocean, tsunamis are barely noticeable, with wave heights of less than a meter and wavelengths of hundreds of kilometers. But when they reach shallow coastal waters, they slow down and pile up, potentially reaching heights of 10 meters or more. The Mariana Trench region has generated tsunamis in the past, though the historical record is incomplete because the area was sparsely populated until recently. With modern monitoring, seismologists can detect earthquakes within minutes of their occurrence and issue tsunami warnings if necessary, giving coastal communities time to evacuate. The network of seismometers and ocean buoys that make up tsunami warning systems is a remarkable achievement of international cooperation and technology, designed to save lives by providing early warning of these rare but catastrophic events. Volcanic activity is the other major consequence of subduction at the Mariana Trench. The Mariana Islands, which lie on the landward side of the trench, are a volcanic arc, a chain of volcanoes formed by magma rising from the mantle wedge above the subducting plate. As the Pacific plate descends, it carries water trapped in minerals and sediments. At depths of about 100 to 200 kilometers, the increasing temperature causes this water to be released. The water rises into the overlying mantle wedge, and its presence lowers the melting point of the rock, causing partial melting. This magma, being less dense than the surrounding rock, rises buoyantly toward the surface, eventually erupting to form volcanoes. The Mariana Arc includes several active volcanoes, both on the islands themselves and as submarine volcanoes on the seafloor. These volcanoes are monitored by geologists because eruptions, while less common than earthquakes, can be hazardous to nearby populations and to aircraft flying overhead, since volcanic ash can damage engines. Submarine volcanoes are particularly interesting because their eruptions are rarely observed directly, but they can create new islands or dramatically alter the seafloor. There's also a back arc spreading zone behind the Mariana Arc, a region where the overriding Philippine sea plate is being stretched and thinned, allowing magma to rise and create new oceanic crust. This back arc spreading is a complex secondary process driven by the subduction, and it creates a separate volcanic system with its own characteristics. Hydrothermal vents are common in back arc spreading zones, and they support unique biological communities, as discussed earlier. The Mariana Trench, then, is not just a deep hole in the ocean, but a dynamic feature of a living, active planet. The earthquakes and volcanoes associated with it are manifestations of the same processes that shape continents, build mountain ranges, and drive the cycling of materials between Earth's surface and interior. Understanding these processes is crucial, not just for scientific knowledge, but for practical concerns about natural hazards, the safety of populations living in seismically active regions, and ultimately for our relationship with the planet we inhabit. Despite more than a century of scientific study and several manned descents to the deepest point in the Mariana Trench, the truth is that we know very little about this environment. The handful of visits, each lasting only a few hours, have given us tantalizing glimpses, snapshots of a world that exists continuously, changing and evolving in ways we can barely imagine. The Mariana Trench covers an area of more than 2,500 kilometers in length and varies in width, encompassing thousands of square kilometers of seafloor. Yet we've directly observed only a tiny fraction of it, less than 1%. The rest remains unknown, unmapped at high resolution, unexplored by human eyes or cameras. What creatures live there that we haven't discovered yet? Every sampling expedition to the Hadal Zone brings back new species, organisms that are genetically distinct from anything in existing databases, and given how little of the trench we've sampled, it's almost certain that vast numbers of species remain unknown. Some of these might be variations on known themes, another amphipod species with slightly different morphology, another polychaete worm with a different feeding strategy, but others might be entirely novel, organisms with body plans or biochemistries that challenge our existing categories and force us to expand our understanding of what life can be. The possibility of undiscovered megafauna is particularly intriguing. While it seems unlikely that large active predators exist in the Hadal Zone, given the scarcity of food and the metabolic constraints imposed by cold and pressure, we can't rule it out entirely. The deep ocean has surprised us before, with the discovery of the coelacanth, a fish thought to have been extinct for 66 million years until a living specimen was caught in 1938, or the giant squid, which remained almost mythical until relatively recently, despite being one of the largest invertebrates on Earth. Could there be something similarly unexpected in the Mariana Trench, a large elusive organism that we simply haven't encountered yet? It's possible, though the more we learn about the trench's ecosystem, the more it seems that large size is not an advantage there, that the organisms that thrive are small, efficient, and patient. We also don't fully understand the geological processes occurring in the trench. Are there hydrothermal vents in the Mariana Trench itself, not just in the nearby back arc spreading zone? Vents occur where seawater percolates through cracks in the oceanic crust, gets heated by magma below, and erupts back into the ocean, carrying dissolved minerals and gases. They've been found in many parts of the world's oceans, including in some trench environments, but the Mariana Trench itself hasn't been thoroughly surveyed for vents. If they exist, they would support their own unique biological communities and could alter our understanding of the trench's ecosystem structure and energy flow. Cold seeps, where hydrocarbons like methane seep from the sediments, are another feature that might exist in the trench but hasn't been definitively documented. Cold seeps support communities of clams, mussels, and tube worms that host chemosynthetic bacteria in their tissues, and they're found in many continental margin environments. The Mariana Trench, with its thick sediments and complex geology, seems like a plausible place for cold seeps, but finding them requires targeted exploration with appropriate sensors and sampling equipment. The sediments of the Mariana Trench hold a wealth of information that we've barely tapped. Cores drilled from the trench floor could extend back millions of years, recording changes in ocean chemistry, sedimentation rates, and climate. These sediments are archives of Earth's history, and analysing them could help answer questions about past climate events, the timing and impact of asteroid impacts or volcanic eruptions, and the long-term evolution of the ocean and atmosphere. But coring the deepest parts of the ocean is technically challenging and expensive, so only a few cores have been taken, and they provide only a fragmentary record. We don't fully understand how water moves through the Mariana Trench, what the currents are, how water from the trench exchanges with the surrounding ocean, and what timescales are involved. Water in the Hadal Zone is cold and dense, but it's not stagnant. There must be some circulation driven by differences in temperature, salinity, and pressure. Mapping these currents would help us understand how nutrients and organic matter are transported, how organisms disperse, and how the trench fits into the larger pattern of ocean circulation. It would also help us predict how pollutants spread and how changes in ocean conditions, such as warming or acidification, might affect the Hadal Zone. The full extent of microbial diversity in the trench is another frontier. Every sediment sample reveals hundreds or thousands of microbial species, and the majority are unknown, organisms with no close relatives in existing databases. What metabolic capabilities do these organisms have? What genes do they carry? What roles do they play in the ecosystem? Answering these questions requires not just sequencing DNA, but culturing organisms, studying their physiology, and conducting experiments to understand how they interact with their environment and with one another. It's slow, painstaking work, but it's fundamental to understanding life in the Hadal Zone. We're also only beginning to understand how Hadal organisms have adapted at the molecular level. The pressure-stabilizing compounds, like TMAO, the modified membrane lipids, the flexible proteins. These are adaptations we've identified, but there are surely others we haven't discovered yet. Studying these adaptations could have practical applications, from developing pressure-resistant materials to understanding how to design organisms that can survive in extreme environments, whether on Earth or on other worlds. The impact of human activity on the Mariana Trench is another area where our knowledge is incomplete. We've found pollution there, but we don't know the full extent or the long-term effects. Are populations of Hadal organisms declining? Are there species that have gone extinct, or that are at risk because of contamination or other human-caused changes? Monitoring the trench over time, establishing baselines and tracking changes would help answer these questions, but it requires sustained effort and international cooperation. Climate change is altering the ocean in profound ways, warming surface waters, causing acidification, changing circulation patterns, and affecting the distribution and abundance of marine life. How will these changes affect the Mariana Trench? The deep ocean has historically been buffered from short-term variations in surface conditions, but over decades or centuries, changes at the surface will propagate downward. Will warming alter the supply of organic matter to the Hadal Zone? Will acidification affect the animals that live there, even at depths where the water is already naturally acidic? Will changes in deep water formation at the poles alter currents and oxygen levels? These questions are important not just for the trench, but for understanding how the entire ocean system responds to human-caused changes. And then there are the philosophical questions, the ones that can't be answered by more sampling or better technology, but that arise naturally from contemplating the trench. What does the existence of life in such an extreme environment tell us about the nature of life itself? Is life an inevitable consequence of chemistry and energy, emerging wherever conditions permit? Or is it a rare and fragile phenomenon that requires a narrow range of conditions? The Hadal Zone suggests the former, that life is tenacious and adaptable, capable of colonizing almost any niche where liquid water exists and there's some source of energy. What are the limits of life? Is there a depth beyond which life cannot exist? Not because we haven't found it yet, but because biochemistry simply can't function under those conditions. Some scientists think the depth limit for fish, around 8,200 to 8,500 meters, might represent such a boundary, but other organisms, amphipods and microbes, live deeper. Is there a depth limit for all life, or could organisms exist even in the crust beneath the seafloor, in the rocks and sediments, kilometers below the trench bottom, living at pressures and temperatures that would seem incompatible with biology? And what about other worlds? The Mariana Trench is often compared to the subsurface oceans thought to exist on moons like Europa, one of Jupiter's large moons, or Enceladus, a moon of Saturn. These moons are covered by thick ice shells, but beneath the ice, liquid water oceans may exist, kept liquid by tidal heating from their parent planets. These oceans would be dark, cold, and under high pressure, conditions not unlike the Hadal Zone. If life exists there, it would likely be microbial, perhaps similar to the chemosynthetic bacteria found at Earth's hydrothermal vents. Studying the Mariana Trench, understanding how life survives there and what strategies it uses, helps us formulate hypotheses about what life might look like elsewhere in the solar system and how we might detect it. The Mariana Trench, in its vastness and its mystery, reminds us that Earth is still a planet of discovery, that we don't need to look to the stars to find the unknown. It's here, beneath our feet, hidden in the depths of the ocean. Every answer we find in the trench raises new questions. Every expedition reveals how much more there is to learn. It's a humbling and, in its way, a hopeful realization. We're not finished with exploring our home planet. There are still frontiers here, still mysteries to solve, still wonders to discover. As you drift towards sleep, consider the Mariana Trench, not as a distant abstract place, but as a real physical environment that exists right now, kilometers below the surface of the Pacific Ocean. There are amphipods moving across the sediment, searching for food. There are bacteria in the ooze, processing organic matter. There are processes we don't understand, organisms we haven't named, secrets waiting to be revealed. The trench is patient. It's been there for millions of years and will be there for millions more, holding its mysteries quietly in the darkness and the pressure and the cold. And perhaps that's the final lesson of the Mariana Trench, that Earth, for all our knowledge and technology, for all our satellite maps and genetic sequencing and deep-sea submersibles, remains in many ways unknown. We live on a planet that can still surprise us, that still holds places where human presence is rare, and life exists on its own terms, adapted to conditions we can barely tolerate, even with our technology. The trench is a reminder of nature's creativity, of life's resilience, of the beauty that exists in even the most extreme and challenging environments. Sleep peacefully tonight, knowing that even in the deepest, darkest, most pressurized corners of our world, life finds a way. Dream deeply and let your mind wander through those alien landscapes at the bottom of the ocean, where evolution has written stories of adaptation and survival in the bodies of creatures we're only beginning to understand. Remember gently that Earth is vast and full of wonders, that mystery still exists, and that the unknown isn't something to fear, but something to cherish, a gift that keeps our curiosity alive and reminds us that there's always more to discover. Thank you for joining us here on Whispering Universes for this journey to the Mariana Trench. Until next time, rest well, and may your dreams carry you to places both familiar and strange, where the boundaries between the known and unknown blur like the twilight zone between surface and abyss.